let's discuss derivatives of logarithmic functions and of exponentials. So derivatives of logs and exponentials. Now I'm going to only talk about base E in this. So base E. They're the easier ones, and we'll get to the harder ones later. So first of all, what is d dx of the natural log of x? Well, it is 1 over x. You might notice that with the power rule, you never got 1 over x. This is the only one like it. So you've got the derivative of the natural log of x is 1 over x. d dx of e to the x is itself. Again, something kind of interesting. The only other function that has derivative equal to itself is 0. So we've got those two. Now what happens if it's more complicated? Well, we have to apply the chain rule. So let's try some examples that way. So d dx of, let me take the natural log of 3x squared plus 5x plus 6. From log properties, you will notice that when you've got the log of something added, you can't do anything with it. You cannot simplify it. So this is stuck, but the derivative of it is 1 over all this. So 3x squared plus 5x plus 6. But then times the derivative of the inside, chain rule. So times 6x plus 5. So we end up with 6x plus 5 over 3x squared plus 5x plus 6. That's our derivative. What happens if you've got d dx of e to the 3x plus 1, let's say? Well, the derivative of an e function is itself, 3x plus 1. Then you have to go in and find the derivative of the exponent. So it's multiplied by 3. So now, if we've got an exponential or a log, we know how to take the derivative. The chain rule applies every single time. Well, let's see some things that are kind of interesting in this. Let's try some exponentials and logs with trig functions. We might as well throw them all together. So let's take d dx, and I'm going to put a product or quotient and chain and some things like that. So let's take d dx of e to the 4x times the cosine of 3x. You'll see some things like this in Calc 2. They won't be asking you to find the derivative, but you'll see some combinations like this. Look at this. This is a product. So since it's a product, I'm going to label this one f of x and this one g of x. My formula for the derivative of a product is f prime of x times g of x plus, product plus, f of x times g prime of x. So what's f of x? F of x is e to the 4x. So f of x equals e to the 4x. So f prime of x is e to the 4x times 4. So I put that there, 4e to the 4x multiplied by g of x, product, okay? Cosine 3x. Then I put plus, f of x is e to the 4x, then g prime of x. What's the derivative of this? Well, that's a chain rule problem. Derivative of cosine is minus sine of 3x multiplied by the derivative of the inside, which is 3. So our result has e to the 4x in both parts, but one of them's got a sine and one's got a cosine. So we could factor it out a little bit. We could say it's e to the 4x multiplied by 4 cosine 3x, and then minus 3 sine 3x. And so there's your derivative. Let's find a derivative function with logarithms and sines and cosines. So let me take d dx of the natural log of the cosine of x. This is something that you might find sort of interesting, you might have wondered about. So if I take the derivative of a natural log, that's the outer function, it is 1 over this, cosine x, times, I've got to do the chain rule, so what's the derivative of cosine? It is minus sine x. Notice the answer to that, it's negative tangent x. We have never been able to get the tangent as an answer to a derivative before. So if you wanted to look at these the opposite way, you could actually integrate now. If you wanted to integrate, and I'm going to take the minus off, but let's just look at this. If I want to integrate the tangent of x dx, then I know what the answer is going to be because I've got this. Now, the answer to integration tends to always have an absolute value in it, so be careful with that. You'll see that when you look up formulas and such. But I've got a minus, so this is going to be minus. I'm going to transfer it to the answer, but then I'm going to do this. I'm going to say it's minus, and then the natural log of the cosine of x in absolute values, and then plus c. Now, why do I do this? We've got to pay attention to a little bit of detail that I didn't go into up here, but if you remember from algebra, tangent functions, or not tangents, exponentials and logs look like this. This is the log, and this one is the exponential. Well, exponential is always positive. Log is not always positive. In fact, it's got a vertical tangent that goes at 0. So if I am looking at some things, you might notice here that log can't be taken of a negative number. So I can't have a negative value for cosine. I've got to have a positive. Well, when I just kind of generally do this, I don't necessarily guarantee that the cosine's positive, because cosine could be as small as -1. So just be aware of that. When you integrate, you get absolute values. When you differentiate, you don't, but when you integrate, you do. Exponentials, no big deal. Just an example of an integral of an exponential. If I take the integral of e to the x dx, guess what? I get e to the x plus c. It's itself. If I take the integral of e to the 4x dx, then I have to do substitution. So let me take 4x equals u, so then 4 dx equals du, and I translate this into u's. So I've got e to the 4x is equal to u, du is equal to 4 dx. Well, I've got to translate for dx, so I divide by 4 here and here. So I've got 1/4 and du. Well, the integral of e to a variable d, that variable is itself. So this ends up being equal to 1/4 e to the u plus c, which is 1/4 e to the 4x plus c. So there's the answer to an integral that's got a substitution in it. So there's a little bit about derivatives and integrals of exponentials and logs.